Good morning, everybody. Today I'm going to give you a few examples of using some statistical mechanics and the concept of the Boltzmann distribution. And then these could be problems that'll be on test 3 or maybe even will help you with your problem set that you're working on now. I'm also going to introduce some concepts behind something called the equipartition function. So this first one, it's just a problem that you could have. Is the following set of states consistent with the Boltzmann distribution? So you can see here we have the energy of some different states divided by the Boltzmann constant. So then you end up with different energy levels being degrees Kelvin, or temperature in Kelvin. So we have a ground state, first excited, second excited, and then the highest state here. So we could to figure out if it's consistent or not, we can look at a ratio between the states. So for example, the population in the first excited state versus the ground state is 17/31, and then ask ourselves, is that equal to what we would expect the ratio for the Boltzmann distributions to be? So here I'm just working with the numerators of the Boltzmann distribution because of course the denominators will be Q, will be the sum over all states will be the same for both states. So the denominators cancel and we just have the numerators of what would be the Boltzmann distribution. And if you plug in these temperatures, so 100 and 0 as your energies, and then what we don't know is what temperature T would that be, such that you have this ratio 17/31. So for the first two, I mean, any two states could be consistent with the Boltzmann distribution. It just would depend on what temperature you're at, right? So 17/31, do some simplification here, take the logarithm of both sides, solve for what the mystery temperature is, and it ends up being 166 Kelvin. So at least for these first two states, if this is your energy gap, to have 31 be in the ground state and 17 in the first excited state, you would need the temperature to be 166 Kelvin. But now we can go through and check the rest of these. Okay, now that we know what the temperature is, how about the ratio of state 1 to state 2? We look at that ratio, we look at the ratio of the Boltzmann weightings, and it ends up being 0.547, which is pretty close to 9/17. So we'd say that checks out, and then we can look at the ratio of the third to the fourth. That's 5 to 9, which ends up being 0.55, which is pretty close to 0.547. So that works out. So we would say this distribution is consistent with the Boltzmann configuration at a temperature of 166 Kelvin. And even at 166 Kelvin, you see some of them are up here populating this state that's equivalent to 300 Kelvin. So we do have, a skewed distribution. All right, here's another problem. So another example. This problem is from England Read, Chapter 30, number 8, but whatever. It's a good problem to think about. At what temperature will the probability of occupying the second energy level be 0.15 for this system? So we have a state where, let's call it the ground state, that's a reference, and then the first excited state is 300 wave numbers. So we're working in different units here. If you wanted to excite your system from 0 to the first excited state, you would need to absorb 300 wave numbers of energy. Okay, what temperature would you have to have so that the Boltzmann distribution lines up with having 15% of the molecules be in the first excited state? Okay, so we can just, if this is all we have for our system, we plug in the Boltzmann weighting for the excited state divided by the sum over the two states, the only two states that exist. Do some math, and there's a conversion that has to happen in here. It's helpful to know that the Boltzmann constant in wave numbers is 0.695038 per centimeters Kelvin. So we can do that conversion factor here so that we can get to temperature, and the temperature is 249. So if your first excited state is separated by that much, it would take 249 Kelvin, a temperature for your population to be 15% in that first excited state. Okay, now this second question, I didn't write down the question here, but basically you can tell from the solution, what if that first excited state is doubly degenerate? So in other words, we need a 2 here and a 2 here if we were to draw a second line up here. So same gap, but we have 2 places that the system can go, whether it be an electron or a oscillator or whatever it is. Okay, so again, probability 15% equal to same expression but with the degeneracies in there. Math, solve for temperature, 178 Kelvin. So it's interesting to compare these two. The effect of degeneracy, as expected, is you don't need as high of a temperature to get population into it, right? Because it'll be more likely that you'll go there if it's doubly degenerate. Another way to put it, as expected, with more high energy states available, the excited states are more easily occupied, so a lower temperature is necessary. More ways to arrange the system such that the excited state is included. All right, and then just a little bit of background. We're headed towards the high temperature approximation and equipartition theorem. We won't quite get there today, but let's think about the different degrees of freedom that we have to work with. So translation, rotation, vibration, and then electronic excitation. So exciting an electron from the ground state to an excited state. And we have models for all of these. So the particle in a box is our translation, the rigid rotors are rotation, the harmonic oscillators are vibration, the hydrogen atom is our electronic. So we can pretty much handle any system using these. So our total energy for the system will be the sum of our energies, and these are all things that we have eigenvalues for: translation, rotation, vibration, and electronic. The total molecular partition function will be the sum over the degeneracies and then e to the negative total energies. And so we can just, if we put in these in the sum, then the way this works is you multiply by all the different degeneracies for the different total states to get the total degeneracy, right? Let's say you had, degeneracies multiply. If you have 2 rotational states for every 2 vibrational states, then you'd have 4 total combinations, for example, right? And this is still just the sum of all the energies. So you can sort these different terms, the way exponents work, so that you can have this be the sum over G trans, e to the negative E trans, and etc., sorting all the different terms. So in fact, this is just the product of all of the different contributions to the molecular partition function. So we can deal with each one of these separately and then combine it again later. That's really cool. That's really powerful. So if we start with just the translational, we know already the molecular partition function for translational is volume divided by the thermal de Broglie wavelength cubed, and the thermal de Broglie wavelength is just this collection of constants. It is a length, and it is amazing that we have Planck's constant in here. The quantum mechanics just keeps coming back. All right, anyway, for argon, for example, at 298 Kelvin, the thermal de Broglie wavelength is 1.60 times 10 to the minus 11 meters. So we're talking about 100th, 200ths of a nanometer. So smaller than an atom of argon. All right, we can do this similarly for rotations. So we know the eigenvalues, where B is a rotational constant, and we know how we get that. Capital I is the angular momentum, moment of inertia, sorry, and we know that. The mu is the reduced mass, we know that. By the way, B has units of inverse centimeters, whereas HCB has units of joules. Okay, so Q rotation, we know has this form. And we know the degeneracies are J 2J plus 1. So we can pop those in there. So our Q is this. And then if we go on the high temperature limit, instead of summing over J, we can integrate over dJ. So high temperature limit means that you have so many rotational states that the distance between them compared to the overall distance is very small. So you're going from basically a Riemann sum to an integral. So anyway, if we can then integrate that, then we can get our Q rotation, and it's a very simple expression, KT over HCB. Wow. All right, but one caveat for rotation, and we'll finish after this, is the rigid rotor. When we did it, we didn't talk about this much, but we assumed that this configuration is different from this, which was true for the system that we looked at in lab, hydrochloric acid, right? If you have hydrochloric acid or hydrogen chloride and you flip it around, it's different to have chlorine on the top versus chlorine on the bottom. But what about for nitrogen? Even if you have a triple bond in here, no, nitrogen and nitrogen are the same. So we have to account for that, double counting. We're counting these as two different states, but actually those are degenerate states if they're the same. So we have to put this degeneracy down here. That's the number of equivalent configurations. That's our sigma for rotation. So for nitrogen it would be 2. Equivalent rotational configurations you should be able to figure out if you think about the symmetry. So like ammonia is, it's a trigonal planar configuration. Trigonal pyramidal configuration. So you can rotate it to 3 equivalent positions, or methane, which is tetrahedral, and that's a little harder to think about, but there are 12 total different ways it could go if the 4 hydrogens are all the same, which they are. So anyway, I'll leave that for today. That's it. So enjoy working on your problem set. It's in Atkins, and I'll see you Friday for collaboration.